Question 9. So this is a classic disproportionation chemistry of chlorine into chlorine minus 1 and chlorine plus 1. So that's chlorine 0. But the HClO, which is actually the disinfecting, it's the disinfectant that does the disinfecting of the drinking water, of your swimming pool water, etc., etc. But it reacts further to give you ClO minus, which is actually Cl plus 1 as well. This is Cl plus 1 as well. This is just dissociation. This is just acid-base dissociation. So what I'm saying is there is no redox because it is chlorine plus 1. This is chlorine plus 1. The hydrogen is plus 1. The oxygen is minus 2. Same thing there. The hydrogen is plus 1. The oxygen is minus 2. Hydrogen plus 1. Oxygen minus 2. So that's why this is not a redox. Alright. So what is the change in oxidation number when forming the ClO minus from aqueous chlorine? From aqueous chlorine, this is your aqueous chlorine, there's chlorine 0, and you want to form ClO minus. So Cl2 to ClO minus, there's chlorine 0 in Cl2, there's chlorine plus 1 in ClO minus. So you want the change. The change is going to be final minus initial. That's going to be plus 1. Okay? Number 10, when you have solid ammonium chloride, it dissociates at a certain temperature in that volume of container. The initial amount of ammonium chloride was 1 mole. So when you have initial mole, you have 1 mole, and you had nothing initially because they told you that you only have this initially, so nothing of that. And then you have mole at equilibrium or equilibrium mole. There's 0.300 mole of it left. Started with 1 mole, but then at equilibrium you are left with lesser, so some of it has dissociated. How much of it has dissociated? Start with 1 mole, end up with 0.30 mole. Therefore 0.700 mole has reacted. Okay, so 1 mole of this react to form 1 mole of NH3. Okay, so you reacted 0.700 mole, so therefore you need to add 0.700 because the mole of NH3 formed is equal to the mole of NH4Cl reacted. Whatever they reacted will form the product. You don't react 0.300, you started with 1, you end up with 0.3 at equilibrium, so you have reacted 0.7. So how much of it has reacted? 0.7 mole has reacted. 1 mole of it reacts to give you 1 mole of this. 0.700 mole of this react to give you 0.700 mole of NH3 because you started with nothing. And then you add 0.700. The same thing with HCl. 1 mole of this will react to form 1 mole of HCl. 0.700 mole of it would therefore form 0.700 mole of HCl. In most cases where the volume is given as 1 dm cube, your life is easy. Here you always have to keep in mind that it is concentration that we use for Kc and not mole. Alright, so in this case, because the volume is not 1, something divided by not 1 does not mean the equal itself. Okay, only when it's divided by 1, then the concentration is the same as the equilibrium mole. So you got 0.300 over 0.500 mole. Mole on top, dm cube at the bottom. That will give you mole per dm cube. Same thing there on the right hand side, mole per dm cube. And then because we know Kc is actually to do with concentration, so Kc is the concentration of NH3 over the concentration of HCl. Times the concentration of HCl because they are both raised to the power of 1 since there's only 1 in their stoichiometric balance equation. Divide by the concentration of the reactant. However, the reactant is a solid. The reactant is not a solution. So what we can say is we don't consider solids to have a concentration. All right. because gas, you can have a concentration, how much of it per the volume, but not solid. So therefore, actually looking back, I would not have to write this down because this is a solid. It doesn't have a concentration, unlike liquid or unlike aqueous or unlike gas. So what we do is we take a value of unit D. This is called unit D as the concentration of a solid always. All right. So looking at solid there. Okay, we take a concentration of unit D. Otherwise, you'll be dividing by no concentration, which is 0. Something divided by 0 is not going to give you a value. So we don't put the solid there because we take a unit D concentration for solids, whether they are on the right or whether they are on the left. So our expression for Kc exclude any solid, only include gas or liquid or aqueous. And that's our final Kc expression. So that is just multiply the two together. 0.70700 divided by 0.500 times by itself, and I get 1.96. The unit, it will have a unit of mole square dm minus 6. At least in the theory paper, they like to ask you the units because it's mole per dm cube time mole per dm cube. Provided you get the expression correct, should be able to get the unit correct. But usually there is error carry forward for the unit because they penalize you for getting expression wrong, provided that your units, you will get error carry forward from whatever expression that you wrote. Okay, so usually error carry forward that way. Yeah. So I guess the trick with this question really is realizing that solids have a concentration of unity, that we don't show solids in Kc expression, and therefore you will get different value if you had taken the concentration of the solid as I showed earlier. Okay, but of course realizing that it's solid, we have a different expression. I go back and change it to being unity. The other trick really is the volume is not 1 dm cube, which most of the time you're given is 1 dm cube, and you'll be nice and happy to just work with the mole. But in reality, when you do this square bracketing, they refer to mole per dm cube. They refer to concentration. What do you think the C for Kc stand for? And what do you think the small p for Kp stand for? That's for pressure, partial pressure. Alright? Question 11. So we have substitution of E10 by chlorine. We are looking for the one with lowest activation energy. Lowest activation energy will mean the fastest. Okay. The first one involve breaking covalent bond. Only break one time ClCl. You are not forming anything at all. You are not forming anything. Okay. I can think of the last one having the lowest activation energy because that involves only forming CCl, not breaking anything. You don't break anything, they just come together, they recombine in their termination step. This is called termination, whereas A is an initiation step, whereas B and C, they are part of propagation, because you have, even though you're forming the same thing here, but here is a termination because radicals and radical recombine to give no radical, whereas this is formed from propagation because radical plus no radical giving you a radical and something else which is not a radical. So essentially you keep on producing radical from another radical. Okay, so there's propagation, but here this involve breaking and also forming bond. So you can work out, if everything is getting gaseous state, you can work out that here you need to break the CH and you are forming the HCl. Here you need to break the ClCl and you are forming the CCl. Here you are just forming bond, which is CCl. Here you are just breaking bond, which is the ClCl. This is just breaking bond without forming any bond. I would say that this is probably the one that has high activation energy, but it's very hard to say because this involves two things rather than just one thing. But what I can be sure is this is exothermic. This is endothermic because you are just breaking bonds, you don't form bonds. You are just forming bond, you don't break bond, okay? But then it's very hard to tell for the option B and option C whether it's endo or exo unless you do the actual calculation based on bond energy, which they like to ask you to do in a paper 2 or paper 4 kind of theory setting. All right. So in terms of lowest activation energy, I would have thought that D is the fastest reaction, not because it's exothermic, because that's to do with thermodynamics, whereas this is to do with rate. Rate and thermodynamics are entirely different things. These are simply lowest activation energy and the fastest because you are just recombining things together. Okay, you are not breaking anything at all. All of these require, A, B, and C require breaking something. Question 12, this is basically atomic and ionic radius. So across the period 3, I hope you know the size of an atom from sodium to chlorine decrease. Of course, it's not linear decrease, but you can have a look at the the data booklet. In fact, you should know the trend that the atomic radius decreased that way. And then the cations are smaller, the anions are bigger. When you form the cations have one lesser shell because Na plus, Mg2 plus, Al3 plus, they all have neon configuration, which of course you know your maximum, your valence electrons is just second shell, whereas this is third period, you're in the third shell and the anions are still in the third shell. So this is n equal to 3. N equal to 3 versus n equal to 2, you can think which one is bigger, alright? Of course, you also need to explain why anions are bigger than the parent atom. Cations are smaller than the parent atom for obvious reason, okay? So, atomic radius decrease across a period due to increasing effective nuclear charge, where you talk about number of protons increasing, nuclear charge increasing, shielding being roughly constant because you go across the third period, you're filling in the same shell, which is the same n equal to 3 shell. So your shielding is roughly constant, but overall your effective nuclear charge increases, so that pulls your outer shell electrons closer together and make your atom smaller. So sulfur is actually smaller than sodium. Sulfur is smaller than sodium, so that's C and D. In terms of ionic radius, your anions will have n equal to 3 shell, so you have S2 minus here, but your Na plus actually has one lesser shell, neon configuration, right? N equal to 2. So your S2 minus is bigger than Na plus. S2 minus is bigger than Na plus. That is argon configuration. That is neon configuration. So sulfur is bigger than sodium for ionic radius. Number 13. So we have solid aluminum chloride sublimes at 178 degrees Celsius. So they're solid going to gas. We know that in Al2Cl6, that is the vapor state. It exists as the dimer as part of your case study. It doesn't exist as the monomer. It doesn't exist as these ions, okay? It exists as a molecule, dimeric molecule, all right? Two of them come together. And this is incorrect because aluminium only is in group 13, only has 3 valence electron, which, you know, uses 1, 2, 3 for bonding. 1, 2, 3 for bonding. How can you have any more electrons when you only use your outer shell electron for bonding, right? Chemistry, not physics. We are not doing nuclear chemistry, we are doing electrons, okay? Valence electron reactivity, all right? So the valence electrons actually come from the chlorine, which donates the outer shell electrons, one of the lone pair to aluminium, another one to the aluminium. This is the concept of dative covalent bond, where the 2 electrons in that single covalent bond come from one atom. These are normal covalent bond. These are not dative covalent bond because in this normal covalent bond, the chlorine donate 1 electrons, aluminium donate 1 electron. They share 1 electron each atom, okay, onto this one covalent bond. Whereas here, the chlorine donates both the electrons for the covalent bond. Question 14, you have an anhydrous calcium carbonate you completely thermally decompose. So this one does decompose when you have calcium carbonate. That gives you calcium oxide plus CO2. So there is the balance equation. The gas is going to be the carbon dioxide, and it started with 0.005 mole of the calcium carbonate, which is anhydrous. That means there is no water crystallization. You get 100 cm³ of CO2. In a separate experiment, you have calcium nitrate. So write another balance equation. So calcium oxide, and then it gives you NO2, brown gas. And when you get this brown gas, you're supposed to test for this colorless gas, which you don't see, but you can test it with glowing splinter. A burning splinter means there's still fire, there's still flame. Glowing splinter, there's no more flame. The glowing splint will rekindle, it will burn, it will start to become burning flame again because oxygen support combustion. So that equation is balanced in terms of stoichiometry. You want what is the total volume of gaseous product from the calcium nitrate. Actually, you don't want from here, you want from the calcium nitrate, okay? So you use 0.005 mole of the nitrate. So I guess we can be looking, because we are looking at gaseous products, even though there are two different cases, but I can think about 2 plus half, which is 2.5 mole of gases. It only works because they are gases, because at standard, at room temperature and pressure, we can be thinking about a specific molar volume, but we don't know that this is at room temperature and pressure. I guess that's why we need this information here. It's at a certain temperature and pressure, so we need to work out the molar volume, okay? Because at that certain temperature and pressure, what is the molar volume, okay? So I guess that's why we actually do need the first bit of information here. So what does that tell us? So we know the mole of CO2. We know the mole of CO2 is to the mole of calcium carbonate. It's just 1:1. The volume of CO2 is 100 cm³, but I want the molar volume. 1 mole of the gas at this certain temperature and pressure occupy a volume of something cm³, because I have used 100 cm³, so I will get the molar volume in cm³ per mole at that certain temperature and pressure. At the bottom will be 0.005 mole. So therefore, what is my molar volume? My molar volume will be equal to 100 over 0.005. So you can work out your rearrangement of equation, and I hope you can see what I'm talking about. So move this up, and then you will have 100 over Vm equal to 0.005. Then make Vm your standard, your subject, okay, your subject of formula. This is 20,000. This is in cm³ per mole. So that is the information that I get at this certain temperature and pressure based on the data given to us. And now I know the molar volume because that is at the same temperature and pressure. So what I can do now is I know 0.005 mole of this reacted. So the second bit of information is the mole of gases, so basically both the NO2 and the O2, over the mole of the calcium nitrate is going to be 2.5 mole of gas is to 1 mole of calcium nitrate. I want the volume, so on the top bit will be the volume of the gases divided by the molar volume at that same temperature and pressure. Oops, it's not 24,000, it's 20,000 cm³ per mole. So that is the volume of gas in cm³ divided by the molar volume at this same temperature and pressure. At the bottom will be the mole of the anhydrous calcium nitrate, so that's 0.005. So the volume of gases is equal to 2.5 times 0.005. Bring up the 2000, so that will be multiplied by the 2,000 as well. Sorry, 20,000. You can do this step by step if you want to, but I think I'm really running out of space on this paper. Okay, so that's 250 cm cube of gases because it produced 2.5 mole of gases. Instead of working individually, both gas will have the same molar volume at the same temperature and pressure as the gas given in the other question. So I can combine them to give me 2.5 mole of gases. And then I'll work out the volume of gases. This paper has been very tricky so far. Yeah? Anyway, number 15. So you have ammonia gas and hydrogen sulfide. They react together to give you this ammonium sulfide. So ammonium sulfide can dissolve in water to give you an orange alkaline solution. Ammonium sulfide dissolve in water to give you an alkaline solution. When you add NaOH, they produce a gas. Well, you have an ammonium SH, you have an ammonium salt, okay? So that is your NH4 plus. Your test for NH4 plus in your qualitative analysis ever since you were 14 to 16 years old doing practical experiments, you will know that when you add hydroxide to something that contains ammonium cation, you heat it, you will get H2O, and then you will get NH3. This is produced as a gas that is pungent smelling. Okay, very easy to spot. You will then test this gas with red litmus paper, which will turn blue. Alright, so this gas is NH3, something you have done in practical a number of times. And then when you add HCl to a separate portion of this solution, it will produce a gas Y. A separate portion of this solution. Well, I mean, it can't be NH3 anymore because your NH3 has been lost. Your NH4 plus is now lost. If you have normal NH4 plus, how do you get this in the first place? You get the ammonium sulfide by reacting this and this. So as this has been given out, you're left just with H2S. So plus moreover, when you add HCl to a separate, hang on. Separate portion. So this is a new experiment. It's a different experiment. That's why it's separate. Okay. What will the NH3 do? The NH3 in this equilibrium, in the equilibrium above, is neutralized. That means it will be removed by the HCl because you're adding HCl. They will remove this. When the concentration of this goes down, so your NH3 concentration will go down. So your NH3 concentration will go down. So this equilibrium will produce more of this, and you have ammonium SH in the presence of acid that can neutralize the NH3 in the NH4 plus. And what they will do, I think, is just give you H2S. Yeah, it will just kick out H2S. Or you can just think about the original situation. You have ammonia gas and H2S giving you this. When I add in HCl, that will remove ammonia gas. That will just give you hydrogen sulfide. So they just H2S. Right? I guess that's one other way of looking at it.